Section 6.4, Part 2, Graphing Transformations of Logarithmic Functions. Transformations of logarithmic functions behave similarly to those of other parent functions. We can shift, stretch, compress, and reflect the parent function y equals log base b of x without the loss of the shape of the parent function. Let's look at graphing a horizontal shift of the function f of x equals log base b of x. When a constant c is added to the input of the parent function, that is the x of the parent function, the result is the horizontal shift c units in the opposite direction of the sign of c, meaning if c was negative, we're going to move to the right. If c was positive, we're going to move to the left. And the transformation is going to look like that. What's going to change? The vertical asymptote is going to shift from 0 to negative c. So the vertical asymptote is going to be equal to negative c. The domain is going to be from negative c to positive infinity. It shifts with the vertical asymptote. The range is not going to change. It's going to be from negative infinity to positive infinity. How about graphing vertical shifts? When graphing a vertical shift of the function f of x equals log base b of x, if we have a constant d that is added to the output of the parent function, in other words, we're going to add it to the whole function, the result is a vertical shift d units in the direction of the sign of d, just like we did before. So this addition is going to shift the parent function up d units if d is positive. It's going to shift the parent function down d units if d is negative. So it follows the sign of d. What is going to change? Because the shift was vertical, we know that the vertical asymptote is not going to change. It is equal to 0. So x is equal to 0 is the vertical asymptote. The domain also does not change, which is going to be from 0 to positive infinity. The range does not change, which is from negative infinity to positive infinity. Graphing stretches and compressions of f of x equals log b of x. When the parent function is multiplied by a constant a that is greater than 0, the result is a vertical stretch or compression of the original graph. For any constant a greater than 0, the function f of x equals a logarithm base b of x stretches the parent function vertically by a factor of a if a was greater than 1. It compresses the parent function vertically by a factor of a if a is bigger than 0, greater than 0, but less than 1, meaning it's a positive fraction less than 1. The vertical asymptote doesn't change. It remains x equals to 0. The x-intercept is 1 and 0. We know that. It doesn't change either. The domain doesn't change. It's from 0 to positive infinity, x inclusive of 0. The range is from negative infinity to positive infinity, or in other words, all of the real numbers. The next transformation is reflection. Graphing reflections of f of x equals log base b of x. When the parent function is multiplied by negative 1, the result is a reflection about the x-axis. When the input is multiplied by negative 1, the result is a reflection about the y-axis. So we know that from previous transformations. So the function f of x, when we multiply negative x with the parent function, so negative log base b of x, this transformation reflects the parent function about the x-axis. So it's a vertical reflection. The domain is going to remain the same from 0 to positive infinity. The range is going to remain the same from negative infinity to positive infinity. The vertical asymptote remains the same, which is x is equal to 0. These are not going to change from the parent function. How about the other type of reflection? When the function f of x is reflected about the y-axis, or in other words, if we multiply the input of the function with negative 1, that is f of x equals log base b of negative x, this multiplication is going to reflect the parent function about the y-axis. So it's a horizontal reflection, which is going to change the domain. The domain is going to be from negative infinity to 0. So all of the negative numbers, x inclusive of 0, all of the negative real numbers, x inclusive of 0. The range doesn't change. It's from negative infinity to positive infinity. The vertical asymptote also remains the same. It's x is equal to 0. These are the range and the vertical asymptote are not changed from the parent function. So these are basically the 4 transformations when we apply them to the logarithmic functions. We also discussed in the past the effect of the base of the logarithmic functions on the speed on which the graph is increasing. So let's use this example to match the functions to the graph. First, I'm going to look at the functions and I'm going to write down the base next to that function so I can recognize the base when I first look at it. D of x is log of x, which means the base is 10. F of x is the natural logarithm of x, which is base is e. That is approximately 2.718282. And then g of x is log base 2, so the base is 2 is clear here. H of x, the base is 5. And j of x, the base is 25. So by comparison here and by looking, we know that the bigger the base, the closer the graph is going to be to the x-axis, or the faster the graph is going to grow. Because the logarithmic function is an exponential function, and we said with the exponential function, the bigger the base, the faster the exponential growth is going to happen, or in other words, we said the graph is going to be very close to the y-axis. And since the logarithmic function is the inverse of the exponential function, then the closeness is going to happen to the x-axis instead of the y-axis. So by looking here, I can tell immediately that that j of x represents the graph E. Graph E here is the closest graph to the x-axis, which means it has the highest base. So I'm going to say this is E. And then the next bigger number or bigger base is base 10. So d of x is going to match the function d, as you can see here. So the graph d is going to match the function d, again, because the base is the next biggest number. So that is d. The next biggest number is h of x, and that matches c. Hopefully you catch what I'm doing here. And then the next biggest is going to be f of x, which is the natural logarithm, and that is b. And then the farthest away from the x is the function a, which is g of x. That is the lowest base that we have. So that is the order of the graph based on the bases of the logarithm. So we're going to, for the first example, we're going to observe some transformations, identify the transformations, and then match the function to the graph given. I'm going to begin from the bottom because I see that this is the easiest transformation. As you can see, the transformation here is the graph has shifted to the left 2 units. So it shifted to the left 2 units. So it's the parent function. The parent function of the logarithmic function looks like this, and it shifted to the left 2 units, and that will lead me to graph A. So the last one is going to be graph A. The next one from the bottom, this one, g of x equals negative log base 4 of x plus 2. So this first transformation is a shifted to the left 2 units, and then this transformation means it reflected over the x-axis, or a vertical reflection. So in this case, we say there is a vertical reflection, or reflected over the x-axis, and then the other transformation was moved to the left 2 units. So the graph that moved to the left 2 units and then it was reflected over, the parent function looks like this, and then if you reflect it over the x-axis, it's going to look like something like this. Let me do that. It's going to look something like this if you reflect it over, and then if you shift it to the left 2 units, that will match graph C. So graph C matches g of x. Last but not least is f of x equals log base 4 of negative x plus 2. So in order to identify the reflection here, because the reflection has a horizontal reflection over the y-axis, so that is reflection over the y-axis. However, the switch here that happened, we need to identify it in a different way. So we're going to find the vertical asymptote instead. So I will make the argument equals to 0, negative x plus 2 equals to 0, and solve. If you solve this, you get x is equal to 2. So that is the new vertical asymptote. Here is the new vertical asymptote, which means the graph actually shifted to the right 2 units. So it shifted to the right 2 units, not to the left. And the reason for that is because the first transformation was a horizontal reflection. So we have to figure out the new asymptote based on that. Similarly, with the previous ones that we did, we can basically find that x is equal to negative 2 is the new vertical asymptote, which is this line right here. And it matches, but because the transformation here was not a reflection over the y-axis, we were able to identify it just by looking at the addition to the x here. However, when there is a reflection, we will need to come up with the vertical asymptote, the new vertical asymptote, to figure out what happened to that function. So I would say that graph B matches the function f of x, because here is the parent function, and then it got reflected over the y-axis, and then it shifted to the right 2 units, so that matches the graph B. So hopefully that is clear. Next, we're going to graph some logarithmic functions based on the transformations. So before we do that, I will need to establish the steps that we need to follow in order to successfully graph each of these functions. Step number 1 is to find the new vertical asymptote. So find vertical asymptote. How do we find that? We set the argument equal to 0 and solve. That is basically how we find the new asymptote. Step number 2, we're going to find the 0 of the logarithmic function. We set the argument equals to 1. So we find the 0 of the log. We set the argument equals to 1 and solve, because that is how we make a logarithm equals to 0, is when the argument is equal to 1. The last step, we're going to find a key point. We're going to set the argument equals to the base that was given. Okay, so B is the base in this case. So let's try the first one here. We have the function log base 2 of x plus 2. So first we're going to find an asymptote. So I'm going to set the argument equals to 0. So x is equal to 0. That is the asymptote. So I'm going to graph the first asymptote. X is equal to 0 is the y-axis. Here I'm going to highlight it. So I graph the first asymptote. Next, we're going to set the argument equals to 1 to find 0. So we're going to say x equals to 1. If you set x is equal to 1, you will get y equals 2 log base 2 of 1 plus 2. So you're going to get 2. So the is 1 and 2 in this specific case. I'm going to graph it. 1 and 2 is approximately here. Lastly, we're going to find a key point, which is by plugging the x equal to the base. So we're going to have x equals to 2. That will lead to y equals log base 2 of 2 plus 2. That is 1 plus 2 equals 3. So the new point is 2 and 3. That is a key point. When x is 2, y is equal to 3. And the graph of the logarithm is going to look like this. So that is f of x equals to log base 2 of x plus 2. Basically, it shifted up 2 units. The x-intercept used to be here. It shifted 2 units up, and that matches the transformation. The next graph, again, I will do the 3 steps one more time. So first you're gonna find a new asymptote. So here is the step number 1, new asymptote. We're gonna make the argument equals to 0 and solve. We get x equals -2. So x equals -2 is this line right here, and that is the new asymptote. Then we're going to find a new 0 by making the argument equals to 1. So we're going to say x plus 2 equals 1. That will lead to x equals to 1 minus 2. So x equals -1. When x is equal to -1, then the y value is equal to log base 2 of -1 plus 2 is log 1, which is 0. -1 and 0. -1 and 0, that is the new 0. And then last but not least, we're going to make the argument equals to the base in order to find a key point. So the argument is x plus 2 equals to 2. That will lead x equals to 0. And when x is equal to 0, y will be equal to log base 2 of 0 plus 2, which is log base 2 of 2, that is equal to 1. So the new point or the key point is when x is 0, y is equal to 1. So that is the key point right here. And the graph of that function is going to look something like this. So this is log base 2 of x plus 2. And it matches the transformation, as you can tell here. The graph shifted to the left 2 units, and that is exactly what happened here. Lastly, I will do the 3 steps one more time. So since I don't have a space, I need to erase some of my work. Hopefully you took notes. And then last but not least, step number 1, I will make the argument equals to 0 to find the new asymptote. So x minus 2 equals 0. That will give me x equals to 2 is the new asymptote. That is the new vertical asymptote. Then I will set the argument equals to 1. So x minus 2 equals 1. That will lead to x equals 3. When x is equal to 3, the y value is going to be negative log base 2 of 3 minus 2 is 1 plus 2. That is 0. So y will be equal to 2. So the new 0 is going to be 3 and 2. When x is 3, y is 2. And then we're going to find a key point by setting the argument equals to the base. So x minus 2 equals to 2. That will lead to x is equal to 4. When x is equal to 4, we have y equals to negative log base 2 of 4 minus 2 is 2 plus 2. That will lead to -1 plus 2, which is equal to 1. So y equals to 1 in this case. So 4 and 1. When x is 4, y is 1. And the graph of the function is going to look like so. If we find the x-intercept, we're going to set 0 equals to negative log base 2 of x minus 2 equals plus 2. That will lead to -2 equals negative log base 2 of x minus 2. Negative gonna cancel with negative. So in this case, we have base raised to the answer equals x minus 2. If we solve, we get 4 equals x minus 2. That is x equals 6. So to be more precise, it's actually going through, it's gonna go through the 0 and 6. It's not. It's going to go through this point right here. Okay. And that is the graph of the last function. Last but not least, applications. These equations are used to determine loudness, advertising response, growth, earthquake, magnitude, decay, pH in chemistry. Example, students in the accounting class took a final exam and then took equivalent forms of the exam at monthly intervals thereafter. The average student score, S of t, as a percent after t months was found to be given by the function S of t equals to 78 minus 15 log base 10 of t plus 1, such that t is greater than or equal to 0. What does 78 represent in this function? So 78 basically represents the initial score of the student, because with the time is 0, when in month 0, you can plug the t is equal to 0, you will end up with this term canceling. So S when t is equal to 0 is basically 78, which is the initial score of the student. What was the average score after 2 months and after 1 year? So after 2 months, that means t is equal to 2. We're going to plug it in. So S when t is equal to 2 equals to 78 minus 15 log base 10 of 2 plus 1. And you can compute that. 78 minus 15 log base 10 of 3, approximately 7.84. I'm going to round it to 2 decimals. And then after 1 year, we know that t is equal to 12 months. So S when t is equal to 12 equals to 78 minus 15 log base 10 of 13. And that is going to be approximately, after you do the math, it's going to be approximately, I will also round it to 2 decimals, it's going to be 61.29. So that is an application, that is A, and this is B, and that is part of B as well. This is the end of section 6.4. If you have any questions, let me know.